Welcome back to the Advanced Microcontroller series. In today's session, let us discuss about the communication protocol. See, in the previous session, we discussed about the introduction, interface, hardware configuration. In today's session, let us discuss about the data transmission. Before that, in the previous session, we tried to discuss about the Minicom, right? Minicom serial terminal. We tried to open that, but I am facing that some issue with that. So today I have fixed that issue. Now it is correctly opening. So now here I am going to type something. Welcome. Are you able to see? No, right? So let me open PIC microcontroller, PICSimLab. So here I am going to load this hexa file. After that I am opening this Minicom serial terminal. So here I am able to see the UR test code. I am able to see. Why? Because it is added in our code, isn't it? So now I am going to type something like welcome. Now are you able to see what I typed? The same thing, are you able to see? Yes, right? So this is what Minicom serial terminal. So some of the Windows platform having this issue with printing strings in the QCOM. Sometimes it will eat one byte. Like for example, I want to print the reset. So it will eat one byte, and there may be a chance to print like that. Okay. So to prevent that issue in Windows, you can go with the Teraterm. For Linux people, it supports, QCOM supports, as well as if you wanted to communicate with the other serial terminal, then you can go with the Minicom. So that's about the Minicom, and let's come with our SPI protocol, data transmission. So let's see how the data transmission happens between master and slave. So here you can see we having master and slave. So this is how the communication happens. So it look like a circular buffer. So every device is going to have a shift register. So if you see the internal of this, here you can see it have a connection like this. So in UART also we couldn't write data directly, or you can't write data directly, or you can't read data directly. So we had a shift register in UART also. The same thing here also in the SPI protocol we having shift register, and we are going to do the operation. Either it can be transmitting or it can be receiving. It happens with respect to the shift register. So in shift register what will happen? Data just gets shifted, right? So here you can see we having a shift register. So this is what shift register. In master and slave, in both side we having a shift register, and connection is like a buffer, circular buffer. So you can see the last bit, which is the last bit of master. You can see this last bit is going to sit at this particular position here, and this bit is going to sit at this particular position. So this bit and this bit is what? MSB of master and MSB of slave, and these two bits are what? LSB of master and MSB of slave. So this is acting like a circular shift. So anything what gets transmitted out of MISO is comes to the slave. the MSB of the master comes to the LSB of the slave, and MSB of the slave comes to the LSB of the slave. So they has been connected in a circular manner, and data gets shifted in a circular manner. So anything we push out of the master is going to get placed in slave. So physically there is a interconnection happens. So if we push anything out of the master is going to get a place in slave. So if we push anything out of the slave is going to get a place in master. Same thing, vice versa. So now I want to shift this. Okay, so here we having data, and this is the MSB and this is the LSB. Okay, and this one find it place in this particular position, and this one find it place in this particular position. So whatever is there in MSB of the slave got shifted to the LSB of the master, and whatever is there in MSB of the slave is going to shift at the MSB of the master. Slave is going to shift at the LSB of the master. So how the shift happens, let's see now. The same data I have taken, so this will going to get a place in this particular position, and this will going to get a place in this particular position. So this one become this one, and this 0 will come to here, then it will become 0 and it will become 1. So what about remaining data? So the same thing, it will come to here, then it will become what? 0, and this will come here, it will become 1, and this will come here, it will become 0, and this 0 will come here, and here one more 0 is there, then again here 1 and here 1, and same thing here also. So this 0 will come here, and this 1 1 1 0 1 1. So let's check whether we got data is same or not. Let's check. So here we having the output same, right? The same data we got. Again do the same thing. So the MSB of the master will comes to LSB of the slave. MSB of the slave is comes to LSB of the master. Let's see whether you got the same or not. So this 0 will come here, and this 0 will come in place of 1, and remaining data is get shifted. And same thing we have to do again. So we have to do 8 times. Same thing we have to do. We have to replace the MSB of the master with the LSB of the slave. The same thing we have to do. So here we have done how many times? 8 times we have done, and finally we got this data. Let's see whether we having the data is same or not. So here you can see 0 0 1 1 1 0 1 1 and 1 0 1 0 0 0 and 1 1 1. Same data we got. But one thing you have to observe here, 1 0 1 0 0 0 1 1 1, which you got in the slave, that is same, right? What we had in master, that only we got in slave, and what we had in slave, that we got here in the master, isn't it? This is how the shifting operation happen. So it is going to exchange the data between the master and slave with the help of shift register, isn't it? So after 8 time, if I shift, can I receive the correct data? No. So here master is transmitting and slave is receiving, and so here you can see master is transmitting and slave is receiving, and slave is transmitting and master is receiving. So Here we achieved the full duplex communication. So at the same time, master is transmitting, slave is receiving, and slave is transmitting, master is receiving. So here we achieved the full duplex communication. Both transmission and reception happens with respect to the clock pulses. So here communication is happen between the master and slave with respect to the clock pulses. But how the clock pulse is getting generated? So now what is our question means how the clock pulse is getting generated. Who is going to generate the clock pulse? Master is the one who is going to generate the clock pulse. And every time whoever is being transmitting and whoever is being receiving, it should happen with respect to the clock pulse. And this clock pulse by the master can be generated in two ways. So, one with the help of built-in peripheral. So, there is two ways. One with the help of built-in peripheral. So, if there is any SPI protocol block which is being present in your microcontroller, it is going to generate the clock pulse. So, if the SPI protocol is not being, then in microcontroller, so your microcontroller is not supporting SPI protocol, and still you want to achieve the SPI protocol, then you have to externally generate a clock pulse. So how to generate clock pulse externally? That we have discussed in the previous session, in the earlier session, right? So by using bit banging method, we can achieve this. So using the bit banging method, you are going to generate a clock pulse, and with respect to that clock pulse, the communication is going to happen. And to achieve this shift, you might have to go with the for loop. Shift the data bit by 8 times. So like this way, you are going to transmit the data in SPI protocol. If transmission and reception of data in SPI protocol, so if there is no built-in clock available, then you are going to generate clock pulse using bit banging method, and you are going to transmit the data or receive the data using the shifting operation, which you are going to achieve by writing a for loop. If the built-in peripheral is already present, so you have a microcontroller which supports SPI protocol, and it has a built-in block for the SPI protocol. Now let's assume I want to transmit some data, and I already got a built-in peripheral at the SPI protocol. So now we have transmit the data, but you can't write the data directly to the shift register, right? So in that case, we will go with the buffer register. So let's assume you having one buffer register. Okay, so I want to transmit some data, like for example 0xxx. Okay, no need xx. 0x11. So I'll go with the buffer register, and I'll write the data into the buffer register. So the moment you write in shift that buffer register, and the instruction get executed. So assume I am having one buffer register, and I am going to write 0x11. So built-in SPI block is going to generate 8 clock pulses, and then this data is being written into the shift register, and using that shift register, the data gets automatically shifted from the master to slave or from the slave to master. So we have to wait until the shifting operation is done. And how are you going to wait? Or you either can do it with the polling method or you can go with the interrupt method. So how to wait we discussed in the previous session, right? The same thing here also you can do. You can do it with the polling method or you can go with the interrupt method. So like UART, here also we having one bit and using that bit you can either go with the polling method or either go or interrupt method. So that is how the built-in SPI protocol block will work. There is no built-in SPI protocol is going to be present. Then you have to what to do? Whoever is transmitting, the aim is just to transmit. So what he gets is least bothered. For example, slave want to transmit the data. So here slave want to transmit the data and slave make the data is being reached the master and whatever slave is getting back is least bothered. And when it is transmitting, whatever it is received is the least bothered. So this is how the SPI protocol is being working. You can either make use of built-in SPI block or you can go with your own SPI protocol implemented. So these names, so here I'm going to show this. So here you can see we having names MOSI, MISO, SCLK. So these names are there, right, which are the name given by the Motorola and we have to stick to the same names. But here in the slave you can see we having some different name SDI, SDO, SEK and CS. So these are the name which are being given by manufacturer of the slave. So this will never going to be a master. So manufacturer wants to tell I am a slave manufacturer and I am definitely sure this will never going to be a master. So why to call master out slave in and master in slave out? Because this is never going to act as a master. That's why slave manufacturer given this name. So what do you mean by SDI? What do you mean by SDO, SCK and CS? So SDO means slave data out. SDI means slave data in. And this is what? Serial clock and this is CS, chip select. So this is about the data transmission. And here these names are given by the Motorola company. So SPI protocol is developed by the Motorola company, right? So what you are going to do, you are going to transmit the data and receive the data, and this supports full duplex protocol. And here we having clock line. The first one transmit, which means data is being written, data write, and second one is what? So first one is, okay, let me read this, okay. Yeah, first one is transmitting, which means data is written, and second one is reception, which means the data is being read. So with respect to the single clock line. So when will be the transmission happen and when will be the reception happen? For clock line we having two level, either it is low level or high level, and also it can be with respect to the edges. So that is what falling edge or rising edge. At the same level there is not will be both of the things will happen at the same level. So one level is dedicated for transmission and other level is dedicated for reception. And here this SPI protocol is an edge triggered protocol. So whenever the clock line falls from the high to low, so here you can see this is the clock line which falls from high to low. So let me use some different color so that so whenever clock line falls from high to low, there is a data being written, but whenever clock line falls from high to low, there is a data being written. All the devices are going to write the data, and whenever there is a transition from low to high in the clock line, so here you can see transition is going from low to high. So in that time what will happen? All the devices are going to read the data. So here all the devices are going to read the data, but here all the devices are going to write the data. Same thing here, you can see. So when is the write happening or read happening? Write is going to happen whenever clock line is falling from high to low and data will be written in that case. And whenever there is a data flows from low to high in the clock line, all the devices are going to read the data. So this is about the data validity in SPI protocol. So there is only one clock line, and with the help of clock line both transmission and reception happens. Before that we discussed about the hardware configuration, in that single master single slave, single master 3 slave, and this daisy chained configuration. We discussed about this, right? So this is what normal configuration and this is what daisy chained configuration. So whenever you go with the daisy chain configuration and whenever you go with the normal chain configuration, so if there will be more number of slave present, there will be more number of hardware lines, means when there will be more number of slave present, then we want the more number of slave select lines. The hardware complexity is going to increase. So in order to avoid the hardware complexity, you might go with the daisy chained configuration. So that is the one disadvantages of normal configuration. So assume, let's take some master and some slaves in both the cases. Both cases means normal configuration and daisy chained configuration. So now master is going to generate the clock pulse and master is taking 1 microsecond for generating every clock pulse. So now master is going to generate a clock pulse and it takes 1 microsecond. So let me write it again. So like this way master is going to generate a clock pulse. Same thing it will happen. It will take 1 microsecond for 1 pulse. To transmit 8 bit of data, how many clock pulses needed? 8 clock pulses are needed. So I want to transmit, and transmission happen only when there is transition from higher to lower level, so that at the falling edge, so every bit get transmitted. To generate 1 clock pulse, master is taking 1 microsecond. To transmit 8 bit, then 8 clock pulses are needed, isn't it? So it should take 8 microsecond. Let's say I want to transmit 8 clock pulse to slave. So for that it will take 8 microseconds. Here I am going to select slave 1 using SS1. So I am taking this example. And to transmit 8 bit of data from master to slave, I am going to make use of 8 clock pulses. And in just 8 microseconds, I make sure the data transmitted from master to slave. So how much time? So how much time it takes? 8 microseconds, isn't it? And what about slave 2? There is a master who wants to transmit 8 bit of data from the master to slave. It takes 8 microseconds to transmit from the master to slave 2. Same thing. And master is going to select slave 2 using SS2, slave select line. The moment it transmits the data, it generates 8 clock pulses with every clock pulses. So 1 bit gets transmitted. To make sure master is transmitted 8 bit of data to slave 2, it again takes 8 microseconds. Here also it takes 8 microseconds. Then what about slave 3? If master wants to transmit the data to slave 3, it takes 8 microseconds. Master wants to transmit 8 bit of data to slave 3. To make sure master is transmitted 8 bit of data to slave 3, it takes 8 microseconds. So in the normal configuration, we can say that point-to-point communication happens. So any number of slave you can take, it is going to take the same amount of time to reach certain data. So you can take 100 slaves. So it take 100 slave also to transmit data from master to slave. So it takes only the 8 microseconds. But what will happen in daisy chain configuration? Master is the one who is going to generate a clock pulse. To generate one clock pulse, master is taking 1 microsecond. Let's say there are 8 bit of data to be transmitted from master to slave 1. How much data it is going to take? 8 microsecond of duration, right? It is going to take. So now master want to transmit some data to slave 2. So it wants to transmit 8 bits of data. To make sure 8 bit of data have reached from master to slave, it takes 8 microseconds. So in daisy chain configuration, what will happen? It will send the data to slave 1. So it takes 8 microseconds. Then slave 1 will transmit the data to slave 2. Again it takes 8 microseconds. So how much total time it takes? 16 microseconds, isn't it? So how did you get? There is no point-to-point communication happening. Master transmit 8 bit data from master to slave 1 using 8 clock pulses. Then again it transmits from the slave 1 to slave 2. So it need 8 more clock pulses. So it takes 8 plus 8. Total 16 microseconds. What about slave 3? It takes 24 microseconds. From master to slave 1 it takes 8 microseconds. Then slave 1 to slave 2 it takes 8 microseconds. Then slave 2 to slave 3 it takes 8 microseconds. 8 plus 8 plus 8 total 24 microseconds it will take. So whichever you want to go with the now for example, so you want to transmit any slave like slave 1 or slave 2, slave 3, you have to do this type only. You have to go slave 1 then slave 2 then slave 3, isn't it? So it takes more time. So whenever you want to go with the point-to-point communication, then you have to choose normal configuration. And when you want to go with a point-to-point communication, then to happen there is a time criteria. So then you can go with the normal configuration. You can save the time also, right? Here there is a point-to-point communication. No need to go here. You can directly communicate. You can save the time. Then you can go with the normal configuration. But whenever you don't want point-to-point communication and okay with any time constraint, and you want the hardware configuration to be reduced, and you okay with any given time, then you can go with the daisy chained configuration. So now there is a single master who wants to communicate with 3 slaves. So let me tell 2 scenario. Okay, so let's say there is 3 temperature sensor. Means what? 3 same slave we having, and what is the second scenario? We having 3 different slave. So in the first case, assume we having 3 temperature sensor, but in the second case we having RTC, double EEPROM and some other sensor. So in the first scenario, which configuration you are going to use? Daisy chain or normal configuration? So now example, you want to buy, so okay, you want to buy 3 temperature sensor. Then you go with the same manufacturer or different manufacturer? Same, right? Connecting to same temperature sensor are easier compared to the different temperature sensor. So same slaves have good compatibility. But second case, what will happen? And before that, here we having one more thing. So once I got instruction set, I don't have to be learn extra number of instruction. That is the reason for choosing daisy chain configuration. But in case of second scenario, so there is 3 different slaves, then we can go with the normal configuration. Why? Because anyways I have to learn 3 different instruction set, and I am definitely not make sure how compatibility between the 3 devices with each other. So making to connect one slave with the other slave with the other, that quite risky. So at times when I get 3 different slaves, I am go with the normal configuration. So in normal configuration, we have go with the 3 different slave select line, and we are going to configure separately instead of interconnected to each other. And there is a point-to-point communication. Now, how to make sure a particular data written into a particular slave using daisy chain? Because there is no point-to-point communication. So now if I want to transmit the data from master to slave 2, so how it will be transmit? So it will transmit to slave 1, then slave 1 to slave 2. But how to make sure data written just to slave 2? So I don't want to write it to slave 1. So let's say you got a device. So let's assume you got a device. So So let's assume you got a device. Okay. So there are 3 DAC inside. One is slave 1, slave 2 and slave 3. So what we have inside, we have 3 DAC and inside we having 3 slaves. So sorry, 3 DACs. One device which having 3 DACs, slave 1, slave 2 and slave 3. Connection is in daisy chain configuration. Signal here we having is digital signal converted to a analog signal. So let's assume I having one microcontroller. Okay. So here what I am having is one microcontroller I am having. So and I am having 3 slaves. So slave 1, I am having slave 1, then also having slave 2 and I am having slave 3. So this is what my microcontroller, and this is slave 1 and slave 2 and third one is the slave 3. So how the connection? So here in the daisy chain configuration, master to slave 1, slave 1 to slave 2, then slave 2 to slave 3, then it will go back to the master. Like this connection, isn't it? So assume clock line is connected. Okay, I am not going to connect the clock line again. So this master is having some garbage value. So for example, it's having some garbage value like 1C, and also these slaves also having some garbage value. So assume it is 1D and this is what 1. So assume it is 1F and we can say it is nothing but let me consider 2D. So like this way it having some garbage value. So we have total 3 DAC, isn't it? Now I want to set the value. It should be high for the slave 2. So to set high, what I have to do? I have to write 1xFF to the slave 2, isn't it? I need to write 1xFF to the slave 2. We don't have access to directly write into slave. Master has to transmit to slave 1, then it will transmit to slave 2. I have built-in SPI block with me and I am going to write buffer register with 0xFF, and that 0xFF gets written into the shift register of microcontroller and data gets shifted to slave 1, then in slave 1 to slave 2. Then you will get the 0xFF. But that here we have 0x1D, right? That comes to slave 2 in the first case. So whatever here in slave 2, it will come to slave 3. So let me explain it again to understand. So let me explain this again. You might get confused if I write like this. So here you can see the same thing. So what I said means I am going to write this in buffer register. What I wanted to send, that is nothing but 0xFF, isn't it? So I am going to write this in buffer register. Then that 0xFF gets written into the shift register of microcontroller and data gets shifted to the slave 1. Now here I got data. But what will happen? This slave 1 is shifted this data to slave 2. So here what we will get? 0x1D. And here what you will get? 0x1F. The slave 2 shift this to slave 3. But what I wanted to get 0xFF to slave 2, right? Again I want to do the transmission. So this should come here, isn't it? but here what you will get, this will get here, 0x2d you will get here, and this 0xFF will come. So before that, master will transmit the data to slave 1. You got the data, and this slave 1 will transmit the data to slave 2, and this slave 2 transmit the data to slave 3, and slave 3 transmit the data back to master. I hope you get it. Now we have achieved what we get. We achieved. What is our aim? We have to write 0xFF to slave 2, and we got that 0xFF in slave 2 we got, isn't it? So now we changed the value of DAC1 and DAC3 as well, isn't it? While writing this to slave 2, we also changed the value of DAC1 and DAC3. Initially it is this value, and now we changed this. So we changed this to value as well, but I don't want to change the value of slave 1 and slave 3. So what to do? We changed this value also, right? While changing this, other two as well changed. We changed other two as well, and it is not preferable. So how we are going to achieve this? We generally take one array, and so let's take one array. So here I am going to take one array. After I go with the array. Now initially master having what value? This one, 0x1c, and slave is having 0x1d, and this is slave 2 is having, and this is slave 3 is having. So whenever I want to write into specific slave 1 or slave 2 or slave 3. So whenever I want to write into specific slave, I want to make sure whatever value present in shift register, it's being stored into an array. So here in slave 1 what we having? 0x1d having. The same thing I am going to write it in array. And what we having in slave 2? 0x1f we having. The same thing I am going to write in the array. And what about slave 3? What we having in slave 3? I am going to write this in array. So whatever data I want to change, only that value I have to change in this array. I go to the array, and for that slave I will change the value. So now I wanted to change the value of slave 2 to this value, right? So here I am going to change the value to 0xFF. This is what I wanted to do, isn't it? So instead of writing data, I'll go with, so in the previous time what we did, we transmitted data directly, but here now instead of writing data, I'll go with the end value. So how? Let's see that. I'm going to delete this previous data transmission. So this is what our actual data, right? So I'm going to delete this data. So now instead of writing data, I'll go with the end value. How? Let's see. So now what is the end data? That is nothing but 0x2d. Whatever I write in master that will come to slave 1, right? So here I am going to write this data and that will come to here, slave 1, and whatever in slave 1 comes to the slave 2. Here we having 0xnd, it will come to here, and whatever in slave 2 come to slave 3. So what we having in slave 2? So initially we had this data, right? And next we have to change, we have to keep on change to get the data. So here you can see 0x2d will come here, and this will come here, and this will come here. So next what I will write to master, I am going to write this slave 2 value. So this I am going to write to the master. The same data will come here, isn't it? The same data will come here. Then what will happen? This data is there, right? Slave 1 data, that will come here. And this data will come here in the slave 3. Now again we have to transmit one more time. So here what we having, this data. So I am going to write this to master, then it will come here, then this data will come to slave 2, and this data will come to slave 3. So now we got this data. Now we achieved what is required. Now only the value of slave 2 is changed, isn't it? Here you can see initially slave 1 having this value, and same thing we having now also, and here also. So only the value of slave 2 is changed, rest we having the same. So this is how you make sure particular data written in particular slave. Then it is a daisy chain configuration. In our PIC microcontroller we don't have SPI block, so we are not going to the code. So this is about the SPI protocol. So in the next session we are discussing about I2C protocol. So I2C protocol having so many names. You can say that I2C TWI means two wire interface, or you can also say that IC. So in the next session let us discuss about I2C protocol. That's all about the today's session. Thank you all.